Hello, my name is Tanik Supakar Mongkon, number 19.
Hello, my name is Nabadi Balabunsap, number 23.
Hello, my name is Anupong Dalanai, number 26. We are from 511. So this video is all about
Waves! Let's go.
Yeah.
what is wave? The wave involves the transport of energy without the transport of matter. In conclusion, a wave can be described as a disturbance that travels through a medium, transporting energy from one location to another location without transporting matter. A medium is a substance or material that carries the wave. As we can see in the video, the voice vibrates the air inside the cup, which are then transferred to the bottom of the cup. The bottom of the cup passes the sound wave through the medium, which is the string, and so on to the other cup. Next, the particle that we see on the wave is a small localized object or entity to which can be ascribed several physical or chemical properties, such as volume, density, or mass. The progressive wave, the wave front moves through the medium, and the wave propagation is any of the ways in which waves travel, with respect to the direction of the oscillation relative to the propagation direction. As we can see, the particle of the wave moves up and down. On the other hand, the direction of wave moves to the right. Comes to the next part. First, the amplitude. The amplitude is the maximum extent of a vibration or oscillation, measured from the position of the equilibrium. So, what is equilibrium? In physics, equilibrium is the condition of a system when neither its state of motion nor its internal energy state tends to change with time. A crest point is a point on a surface wave where the displacement of the medium is at a maximum. A trough is the opposite of a crest, so the minimum or lowest point in a cycle.
A transverse wave is a wave in which particles of medium vibrate at right angles or perpendicular to the direction that the wave travels. As we can see in the picture, particles of the string move up and down. In contrast, the direction of wave moves to the right, so the direction of wave is perpendicular with the particle which vibrate the string. Longitudinal waves are waves in which the displacement of the medium is in the same direction as, or the opposite direction to the direction of propagation of the wave. In this video illustrates the longitudinal wave in the form of spring. The movement of the particles are in the same direction with the direction of wave. A mechanical wave is a wave that is an oscillation of matter and transfers energy through a medium.
Period is the time for a particle on a medium to make one complete vibration cycle, and cycles are pairs of a maximum value and a corresponding minimum value. Both period and cycle have the same range, which is the starting point to the next starting point. They can be between the crest or trough point, or at the point when the displacement are zero. Lastly, frequency is the number of waves that pass a fixed point in a given amount of time.
In the next pictures, I'm gonna discuss about wavelength, wave speed, and phase difference. Wavelength is the distance from one crest to another, or from one trough to another of a wave. Wave speed is the wave at which a wave travels. And last, phase difference is used to describe the difference in degrees or radians when two or more alternating quantities reach their maximum or zero values.
Electromagnetic waves, or EM waves, are waves that are created as a result of vibrations between an electric field and a magnetic field. In other words, EM waves are composed of oscillating magnetic and electric fields. And all of the electromagnetic waves are all transverse waves, which oscillate perpendicular to the direction of energy transfer. In a vacuum, they have the same speed, which is 3 times 10 power by 8 meter per second. In different medium, they travel at different speeds, and the refraction occur, which is the changes of the direction of the wave. As we can see on the table, we split the electromagnetic waves into 7 basic types, but they are actually all parts of one continuous spectrum. The difference between them is the wavelength and the frequency, where they are inversely related, which means that when the first one goes up and the other one goes down. So as we can see on the table, from left to right, the frequency increases while the wavelength decreases. So the radio wave have the greatest wavelength but the smallest frequency, and the gamma rays have the biggest frequency and the smallest wavelength. Next, we're gonna explain about the energy and matter. Energy in physics is the capacity of doing work. It may exist in potential, kinetic, thermal, electrical, chemical, nuclear, or other various forms. They are moreover heat and work. For example, energy in the process of transfer from one body to another. And the matter is any substance which has mass and occupies space. All physical objects are composed of matter in the forms of atoms, which are in turn composed of protons, neutrons, and electrons.
S-waves are transverse waves, meaning that the oscillations of an S-wave particles are perpendicular to the direction of wave propagation, and the main restoring force comes from shear stress. S-waves can't propagate in liquids, however, they may propagate in liquid with high viscosity, zero or very low viscosity. P-waves travel faster than other seismic waves and hence are the first signal from an earthquake to arrive at any affected location or at a seismograph. P-wave may be transmitted through gases, liquids, or solids.
Next, we're gonna explain about water waves. We can see the water wave move towards the shore on the crest of a wave and move the same distance backward with the trough of the wave. The debris moves in a roughly circular path perpendicular to the water's surface. Water waves are surface waves, a mixture of longitudinal and transverse waves. Surface waves is oceanography are deformations of the sea surface. The deformations propagate with the wave speed, while the water molecules remain at the same positions on average. However, energy moves toward the shore. Most ocean waves are produced by wind, and the energy from the wind offshore is carried by the waves toward the shore. We distinguish between deep water waves and shallow water waves. The distinction between deep and shallow water waves has nothing to do with absolute water depth. It is determined by the ratio of the water's depth to the wavelength of the wave. The water molecules of a deep water wave move in a circular orbit. The diameter of the orbit increases with the distance from the surface. The motion is felt down to a distance of approximately one wavelength, where the wave's energy becomes negligible. The orbits of the molecule of shallow water waves are more elliptical. The change from deep to shallow water waves occur when the depth of the water, d, becomes less than 1/2 of the wavelength of the wave, lambda. When d is much greater than half lambda, we have a deep water wave or a short wave. When d is much less than half lambda, we have a shallow water wave or a long wave. The speed of deep water waves depends on the wavelength of the waves. We say that deep water waves show dispersion, where dispersion is the separation of white light into colors or of any radiation according to wavelength. A wave with a longer wavelength travels at higher speed. In contrast, shallow water waves have no dispersion. Their speed is independent of their wavelength. It depends, however, on the depth of the water. Shallow water waves move at a speed that is equal to the square root of the product of the acceleration of gravity and the water depth. Deep water waves in the ocean are wind-generated waves. They can be generated by the local winds or sea, or by distant wind swell. Ocean waves are produced by a variety of forces. Meteorological forces, which is wind and air pressure, produces seas and swells. Astronomical forces produce the tides. Earthquakes produce tsunamis. Tides and tsunamis are shallow water waves, even in the deep ocean. The deep ocean is shallow with respect to a wave with a wavelength longer than twice the ocean's depth.
Guitar. In guitar string, it is moving because it has just been plucked. Plucking the string gave it energy which it is moving through the string in a mechanical wave. A mechanical wave is a wave that travels through matter. The type of mechanical wave passing through the vibrating guitar string is a transverse wave. The wave travels down the string to the end. The oscillation of the guitar strings travel perpendicularly to the direction of the wave. As a guitar string vibrates, it sets surrounding air molecules into vibrational motion. The frequency at which these air molecules vibrate is equal to the frequency of vibration of the guitar string. The back and forth vibrations of the surrounding air molecules create a pressure wave which travels outward from its source. This pressure wave consists of compressions and rarefactions. The compressions of regions of high pressure where the air molecules are compressed into a small region of space. The rarefactions are regions of low pressure where the air molecules are spread apart. This alternating pattern of compressions and rarefaction is known as a sound wave. A guitar string vibrating by itself does not produce a very loud sound. The string itself disturbs very little air since its small surface area makes very little contact with surrounding air molecules. However, if the guitar string is attached to the larger object, such as a wooden sound box, then more air is disturbed. The guitar string forces the sound box to begin vibrating at the same frequency as the string. The sound box in turn forces surrounding air molecules into vibrational motion. Because of the large surface area of the sound box, more air molecules are set into vibrational motion. This produces a more audible sound. In conclusion, the vibration of guitar string is the transverse wave, and the sound that is produced is the longitudinal wave. Compression is the application of balance inward. Pushing forces to the different points on a material or structure that is forces with no net sum or torque direct so as to reduce its size in one or more directions. Rarefaction is the reduction of an item density, the opposite of compression. Like compression, which can travel in waves, sound waves for instance, rarefaction waves also exist in nature. A common rarefaction wave is the area of low relative pressure following a shock wave.
Next, we're gonna explain the physics of a tsunami. A tsunami, also called Seismic sea wave or tidal wave is a catastrophic ocean wave, usually caused by a submarine earthquake occurring less than 50 km beneath the seafloor, with a magnitude greater than 6.5 on the Richter scale. Underwater or coastal landslides or volcanic eruptions also may cause a tsunami. The term tidal wave is more frequently used for such a wave, but it is a misnomer, for the wave has no connection with the tides. A tsunami can have a wavelength in excess of 100 km and period on the order of 1 hour. Because it has such a long wavelength, a tsunami is a shallow water wave. Shallow water waves move with a speed equal to the square root of the product of the acceleration of gravity and the water depth. The rate at which a wave loses its energy is inversely related to its wavelength. A tsunami not only propagates with a high speed, it also can travel a great transoceanic distance with only limited energy loss. So, what happens when this wave reaches the shore? In the deep ocean, the amplitude of a tsunami is only a few feet. It cannot be felt aboard a ship or seen from the air in the open ocean. When the tsunami approaches the coastline, its speed decreases and its amplitude increases. The power is proportional to the square of the amplitude times the speed. As the speed decreases, the amplitude increases. The amplitude can grow to a height exceeding 100 feet. The tsunami can strike with devastating force. Earthquakes generate tsunamis when the seafloor abruptly reforms and displaces the water above its equilibrium position. Waves are formed as the displaced water under the influence of gravity attempts to regain its equilibrium. The initial size of a tsunami is determined by the amount of vertical seafloor deformation.
Polarization is the attribute that wave acceleration have a definite direction relative to the direction of propagation of the wave. Next is wavefront, a surface containing points affected in the same way by a wave at a given time. Coherence, the quality of being logical and consistent. Next one is superposition. It's a sum of many waves formed in one wave. Cladding, outer layer covering with another material. Path difference, the difference between the distances traveled by two waves meeting at a point. Next, standing wave which oscillates in the time but whose peak amplitude profile does not move in space. Total internal reflection, a complete reflection of a ray of light within a medium. Critical angle, the angle of incidence that provides an angle of reflection of 90 degrees. Interference, the combination of two or more electromagnetic waveforms to form a resultant wave. Constructive, the interference of two or more waves of equal frequency and phase resulting in their manual reinforcement and producing a single amplitude equal to the sum of the amplitudes of their individual waves.